Our topic for today are redox reactions. Redox reactions are chemical reactions in which not only uh, compounds change places, atoms change places, but so do electrons. Electrons are transferred between reactants. These must be paired events. There is oxidation, and it's always paired with reduction. The loss of electrons is called oxidation, while gaining electrons is called reduction. You'll need to be able to identify both halves of these reactions later on. Here's a clue for you. Oxidation number increasing from reactant to product is oxidation, and oxidation number decreasing across the arrow is reduction. In order for you to be proficient in redox reactions, you need to be able to determine the oxidation state of every atom in a chemical reaction. And now there are some rules for assigning those numbers, and we see them here. You need to remember that any atom as it is in its elemental form has an oxidation number of 0. This includes the diatomic elements. So chlorine has, when it is in its elemental form, Cl2, has an oxidation number of 0. A monatomic ion has an oxidation number equal to its charge. That means that any ion in an ionic compound, its oxidation number is the same as its charge. So sodium would be +1 and chlorine would be -1. Oxygen is -2 in all compounds with the exception of peroxides in which it is -1. A peroxide that you will be responsible for, and the only one you'll be responsible for is hydrogen peroxide. In hydrogen peroxide, the hydrogen is +1 and the oxygen is -1. Remember, this is the exception. It's -2 everywhere else. The sum of the oxidation numbers in a neutral compound is 0. So, let's look at the algebra method for assigning oxidation states to all atoms in a compound. If we were to take potassium permanganate, there are 3 atoms in this compound. We would list the atoms. We would count the atoms. There is 1 potassium, 1 manganese, and there are 4 oxygens. Then we would assign the oxidation numbers that we know for sure. This is an ionic compound, so the potassium is equal to its regular charge. That means 1 times +1 is a total +1 charge. The manganese is one of those tricky transition metals. We don't know its charge oxidation number, so we will assign it X. This is not a peroxide, so oxygen is -2. 4 times -2 is -8. When we add these together, since this is a neutral compound, we come up with a little algebra problem. 1 plus x minus 8 is equal to 0. X minus 7 is equal to 0. X is equal to 7. So the potassium has a +1, the manganese +7, and the oxygen -2. It is conventional to write the oxidation number over and slightly to the right of its atom. Now, identifying oxidation and reduction in a reaction. Here we have 2 reactions, aluminum with a +3 charge. This is the clue to you that there is an anion with it, but it is a spectator anion, so it is not in this net ionic equation. This is elemental zinc, so it would have an oxidation number of 0. Elemental aluminum would have an oxidation number of 0, and the zinc ion has an oxidation number of +2. So we're looking at what happens across the arrow. Aluminum +3 goes to aluminum with an oxidation number of 0. The oxidation number is going down, which represents a gain of electrons. How many electrons? 3. And so that is reduction. Zinc, oxidation number increases across the arrow. It increases by 2. That means it lost 2 electrons. Another way to write this, aluminum plus 3 electrons changes into aluminum with no charge. See how the charges balance out? Plus 3 plus minus 3 equals 0, and so does 0 on the other side. So when we look at this example, chlorine, elemental chlorine, has an oxidation number of 0. So does elemental sodium. On the other side of the arrow, sodium has gone up in oxidation number. So the sodium is the species or reactant that is oxidized, while chlorine's oxidation number has decreased across the arrow, so the chlorine has been reduced. It is customary for us to split reactions into half reactions, to look at them separately. Here is an example. Here is our equation, and we have looked and we see that cobalt is oxidized. Its oxidation number goes up across the arrow, and it loses 2 electrons, while iron is gaining 2 electrons to go to elemental iron. Here we have our example problem. We have silver ions, elemental nickel ions, and silver as it is on the periodic table. The oxidation portion of this, we need to find the reactant whose oxidation number increases across the arrow. That would be nickel. Nickel becomes the nickel ion when it loses 3 electrons. Silver gains 3 silvers will gain 1 electron each for a total of 3 electrons, and it becomes 3 atoms of silver. When we balance half reactions, we split the reaction into its parts. We determine what is oxidized. In this reaction, the iron plus 2 goes to iron plus 3, and when it does that, 1 electron is lost. We can see that this is the correct number of electrons because on this side we have plus 2, and on this side we have plus 3 plus a negative 1 is plus 2, so that's the correct number of electrons that were transferred in this oxidation half reaction. In the reduction half reaction, gold plus 3 gains 3 electrons to become gold, elemental gold, without a charge. So the 3 plus charge from the ion plus 3 negative electrons makes 0, and that equals 0 on the other side. We know we have the correct number of electrons being exchanged between this reduction half reaction. So once we have done that, we're good to have our number of electrons balanced, because that is our goal here. The iron only had a transfer of 1 electron, while the gold had a transfer of 3. What we will do to balance that is we will multiply the entire half reaction by 3, distributing the 3 throughout. That leaves us with this balanced half reaction, which added to the reduction half reaction. These electrons at each side of the arrow cancel out, and we are left with this balanced redox reaction. In this case, our oxidation reaction will be Fe plus 2 will go to Fe plus 3 with 1 electron lost. while lead plus 2 will gain 2 electrons to become elemental lead. We can see that we do not have the same number of electrons on each side of the arrow, so we must collectively multiply this by 2 and then add it together, and our balanced redox reaction, when we add these two together, this would become 2, this would become 2, and this would become 2. These would cancel. Our balanced redox reaction would be 2 Fe plus 2 plus lead plus lead plus 2 yields Fe, 2Fe plus 3 plus lead in its elemental form.